Electromagnetic radiation. Electromagnetic radiation includes a whole array of things: visible light, radio waves, X-rays, and a lot more things. And the main point of it is that it's all waves. So when we look at a wave, not a great wave, but still a wave, waves all have three primary characteristics. They all have wavelength, which is measured in meters, which of course should be a lowercase m, not a capital M. Sorry about that. And then anything that modifies it, nanometers is one that's commonly used. And it is the distance, look, from peak to peak. But if we measure trough to trough, we have that same wavelength. Frequency, which is new, is cycles per second. So if we were observing the wave from here, a certain number of cycles, a certain number of peaks would pass in a given amount of time. Okay? So we have a higher frequency in that first crudely drawn wave than in the second one. It also has a shorter wavelength. So you can see that wavelength and frequency are inversely related. Now, all electromagnetic radiation also has a speed, and they all travel at the same speed. And it is the speed of light in a vacuum, which is 2.9978 times 10 to the 8th meters. Sometimes you just see it as 3. Depending on the number of significant digits that you need. So there's our equation. Since the wavelength and the frequency are inversely related, their product is constant, and it is constant as the speed of light. So if we know the wavelength or the frequency, we can find the other one. So we are given lambda, and we want to find nu. So if we divide both sides by lambda, we can plug in our values. So 2.9979 times 10 to the 8th meters per second. However, we don't have meters, we have nanometers. 1 meter is 10 to the 9th nanometers. So 1 nanometer would be 10 to the minus 9 meters. So make it easy on yourself. Don't worry about proper scientific notation because you're going to be plugging it into a calculator. And all you have to do to convert nanometers to meters is tack on times 10 to the minus 9. So you're going to have to remember how to do scientific notation in your calculator. So 2.9979. Remember, second function and then the comma to get the E. And we have a power of 8 on the top. We are dividing that by 589, second function comma to get the times 10 to the part, negative 9th power. And so we get 5.09, because I'm rounding it to significant digits, times 10 to the 14. And look at what the units are. Meters on the top, meters on the bottom. So we're left with 1/seconds, which we can also write as seconds to the -1, so that we don't have to deal with a fraction. But that is the same as the unit hertz, which is abbreviated Hz. So we would write 5.09 times 10 to the 14 hertz. Now, energy can be gained or lost in whole number multiples of h nu, where h is Planck's constant, because it is Max Planck who came up with this idea that energy is quantized. So there is our equation. So we know that energy is directly related to frequency, which means energy is inversely related to wavelength. If we draw some waves here, that one has the higher energy, that one has the lower energy, this one also has the higher frequency and the shorter wavelength. So, if we want to know the energy emitted by that same sodium atom we had before, well, we know that it has 589 nanometers. We know that nu equals c over lambda, because we rearranged that up there. So we can plug that in. Delta E equals h c over lambda. Just plugged in for nu. So we have 6.626 times 10 to the minus 34 joules times seconds times 2.9979 times 10 to the 8th meters per second. So the seconds cancel. We are dividing it by 589 times 10 to the minus 9 meters. So then meters cancel. So our answer is going to be in joules, and we're solving for energy, so that's an appropriate unit. So we have 6.6, oops, 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 589 times 10 to the minus 9. And there we go. We have that our delta E is 3.37 times 10 to the, let's go look back at the calculator and figure out what the power is, negative 19. And our unit is in joules. So why did I go back and use this original given information and not the answer to the last one? Just because there would be less rounding involved. Should have made no difference, though, mathematically, except for a potential rounding error.